The nth term test and the harmonic series. Objectives. By the end of this lesson, you should be able to apply the nth term test to determine if an infinite series diverges and recognize the harmonic series. Alright, the first test that we're going to talk about is the nth term test, and it's probably the easiest test and yet the trickiest test at the same time. So let's take a look. It says, given a series, the sum from n equals 0 to infinity of a sub n, if the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. So what we have to do is we have to look at the sequence of terms that we're trying to add together. If those terms don't get closer and closer to 0, then the series is going to diverge, because there's no way that adding up all of those terms is ever going to be a finite number if those numbers aren't even getting smaller and smaller and closer to 0. So before we even look at what the rest of this page says, let's take a look at an example. We have the sum from n equals 1 to infinity of n squared. So it doesn't matter that this is n equals 1 and that's n equals 0. What we're trying to take a look at is what is happening to the limit as n approaches infinity of n squared. So as n approaches infinity, if I start plugging in really big numbers and squaring them, this is headed towards infinity. So by the nth term test, the original series has to diverge. So this original series diverges because this limit does not equal 0, right? This limit does not equal 0. So let's erase that for a second. So infinity does not equal 0. So if we found out that this limit does equal 0, that doesn't mean that the series converges. So now let's try to look at this. The main idea is that in order for a series to converge, it's necessary for the sequence of terms a sub n to converge to 0. It's necessary for the terms to be getting smaller and smaller and closer to 0. And what's happening to these terms? Let's actually expand this series out. So let's look at it down here. We plug in 1, we get 1 squared, plus 2 squared, plus 3 squared, dot, dot, dot. So this is 1 plus 4 plus 9 plus 16 plus 25. So if I look at the sequence of terms I'm trying to add together, 1, 4, 9, 16, 25. If I look at that sequence is heading towards infinity. So how could I possibly add up all of these terms and get a finite number if these terms are just getting bigger and bigger and bigger? That's what the nth term test says. That in order for the sum, adding up infinitely many terms, in order for it to even have a shot at adding to a finite number, the numbers better be getting smaller, and smaller, in fact, going to 0. So they can't converge to any other number but 0, the sequence of terms that we're trying to add together. So the biggest warning here is that if the limit as n approaches infinity of a sub n does equal 0, that does not mean that the series converges. It just means it has a chance at converging. The nth term test is a failure test only. It does not tell us anything about convergence. It only tells us that the series diverges, or we're inconclusive. We don't know enough yet. We're going to have to try another test as we move forward and learn other tests. So let's look at an example. So in this example, we're asked to show that the following series diverges by applying the nth term test. And the series is the sum from n equals 1 to infinity of 2n plus 1 over 3n plus 2. So just keep in mind, this is not actually what the types of questions are going to look like. The questions are just going to ask you to determine whether or not the series converges or diverges. But for the purposes of this section, we're being told to show that this definitely does diverge by applying the nth term test. So the nth term test says that we're going to take the limit as n approaches infinity of 2n plus 1 over 3n plus 2. Since this is a limit at infinity and the degrees of the numerator and the denominator match, this limit is exactly 2/3, which is not equal to 0. So the only way this series has a possible chance of converging would be if the limit of the sequence converges to 0, but it converges to 2/3. So by the nth term test, and I'm going to abbreviate that as this, nth term test, the series diverges. So let's take a look at another example. In this next example, we're going to show again that the series diverges by applying the nth term test. So n equals 1 to infinity of negative 1 to the n. So what we're going to try to do is show that the limit as n approaches infinity of negative 1 to the n does not equal 0. So what does this look like, negative 1 to the n? So let's write out a few terms in the sequence. So this sequence is a sub n equals negative 1 to the n. So a sub 1 is going to be negative 1 to the 1. So I'll put that in parentheses. Negative 1 to the 1 or just negative 1. And then a sub 2 is going to be negative 1 squared, which is positive 1. And then a sub 3, you'll see we don't have to do too many of these, that's going to be negative 1. So this sequence of numbers is negative 1, 1, negative 1, 1, negative 1, 1, and so on. So as you can see, this limit does not exist. So the limit as n goes to infinity, if I thought about graphing this, which is another great thing to think about, so 1, 2, 3, 4, 5, let's just plot a couple. So at 1, we're down here at negative 1, and then at 2, we're at 1. So this function is just bouncing back and forth. So it's going to negative 1, 1, negative 1, 1, so it's oscillating. So as n approaches infinity, way over here, this limit doesn't get closer to any particular number, let alone 0. This limit does not exist. So by the nth term test, the series diverges. Now, I do want to bring your attention to something interesting. If I were to have written out the terms of this series, so if I were to have written out, let's do it down here, the sum of n equals 1 to infinity of negative 1 to the n, well, that's negative 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And you might be tempted to think that I can do this clever grouping of terms where I say, well, negative 1 and 1 are going to cancel, negative 1 and 1 are going to cancel, negative 1 and 1 are going to cancel because I'm going to get 0, 0, 0 every time. But what if I happen to group them in a different way? What if I happen to say, well, only those two are going to cancel, 1 minus 1, and 1 minus 1, and 1 minus 1, so then I'm left with negative 1. So it turns out that that type of grouping doesn't work, and that's why we do need that formal definition of the limit of partial sums to tell us that that's how to formally determine whether or not infinitely many terms are going to add to a finite number. So here, there was no unique grouping that we could do. So we could have got 0, we could have got negative 1, and it doesn't work out like that. So we are going to use a grouping trick with telescoping series, which is coming up, but this did not give us a unique grouping, so this series diverges. In this example, we're told to try to apply the nth term test to the sum of n equals 1 to infinity of 1 over n. What is the result? So we would start by taking the limit as n approaches infinity of 1 over n. Well, we've seen this enough times to know that this limit does equal 0. All we know at this point is that the series 1 over n from n equals 1 to infinity may or may not converge. Or another way to state that is this is an inconclusive result from the nth term test. So in the future, when we have more tests, we wouldn't be done here. This would just mean try another test. But for now, this is inconclusive. We don't know if it converges or diverges. So based on the nth term test, we just don't know. But to say that this limit equals 0, just by itself does not mean that the original series does converge. We just don't know. We don't have enough information. So this is actually a special series called the harmonic series, and we're going to take a closer look at it next. So the harmonic series is the sum from n equals 1 to infinity of 1 over n, and it turns out that it does diverge, but the nth term test didn't tell us that. So what we're going to do is look at a little proof of why the sum of the harmonic series actually does diverge. So the sum can be expanded to be written out as 1 plus 1/2 plus 1/3 plus 1/4, etc., etc., etc. So we're going to stop at 1/8 because that's enough to hopefully see the pattern here. So what we're trying to show is that adding up all of these terms is not going to converge to a finite number. So even though the individual terms in the sequence of numbers are getting smaller, they're getting closer to 0, they're not getting smaller fast enough so that the infinite series adds up to a finite number. So what we're going to do is we're going to compare number by number, just for the first few, with another series. So what we're going to do is we're going to try to show that this harmonic series is greater than or equal to this series written here below. And if we can show that this series below, which is smaller than the one above it, if we can show that this ends up adding up to infinity or not converging to a real number, then something bigger than it must also not converge or diverge. So number by number, let's compare. So let's make sure that the top line is greater than or equal to the bottom line. So 1 is equal to 1, that's fine. 1/2 is equal to 1/2. So now we want to make sure that 1/3 is greater than 1/4, and it is. So that keeps the inequality. So the top is still bigger than the bottom. 1/4 is equal to 1/4. 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8. And 1/8 is equal to 1/8. So hopefully you can see if I continue this pattern where the next grouping is going to end up being 1/16, that as I continue to move along, I'm going to be able to show with 8 copies of 1/16 that the top series is bigger than each term in the bottom series. So now let's think about this bottom series, which we just said is smaller. So the top, let's just clarify, the top is bigger, the bottom is smaller. So here, well, this part is 1 plus, well, 1/2 is just 1/2, and we're adding 1/2, and we're adding 1/2, and then we're going to have another collection. So we're going to have 8 copies of 1/16 plus 1/16 plus 1/16. So 8 copies of this is going to be 8/16, which is 1/2. And this pattern is actually going to continue so that I have 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And if I keep adding the same number to itself over and over again, it's going to get bigger and bigger and bigger. So this is going to infinity. Adding up the same number to itself is going to go to infinity. And we said that this sum on the bottom was smaller than this one on the top. So if something smaller still goes to infinity, something bigger must also go to infinity. So it's kind of a watered down little proof here, but hopefully it's giving you some intuition about what we're doing. So the harmonic series is the perfect counterexample to why the nth term test is a failure test only. So the limit as n goes to infinity of 1 over n is 0. Each of these terms individually, if I look at the sequence, is going to 0. They're getting smaller and getting closer to 0, but they're not going to 0 fast enough so that when I add them all together, I'm going to get a finite number. When I add them all together, I am going to get infinity.